Yeah. Okay. So what I was telling is that so this is a relation between this JQ and J. So let us first look at the units, and then we'll go to what the observations were. So JQ is the flow of energy per unit area per unit time when delta T gradient of T is 0. So that would be so J is, of course, let's say joules per second per centimeter squared, right? So J would be not J. This small J is joules per second per centimeter squared. Um, yeah. And then gradient of T is, of course, Kelvin per centimeter. So if you put all of those in, what you will find is joule per second would give you a watt. So this W is for watt. And then, so this would be watt per centimeter Kelvin. And what is the unit of sigma? Sigma is simply 1 over rho, where rho is the resistivity, which is resistance time area divided by length. So that is rho is ohm centimeter. And so sigma would be 1 over ohm centimeter. So if you plug the units in, you will get kappa over sigma is, it has units watt ohm per Kelvin. And when you, okay, so that is the unit of kappa over sigma. So let us now go and see what the observations were and what we are trying to look at. We are sort of focusing on this thing because this was one of the striking successes of the Drude theory. And as we'll see, for very strange reasons. So here it is. The experimental thermal conductivities and Lorentz numbers, which are basically this kappa over sigma T. So what do you find at, this is at 0 degrees Celsius, and this is at a room temperature, 373 Kelvin. Let us look at a few numbers. So if I look at copper, for example, this is kappa over sigma T, which is 2.2. And at 373 Kelvin, it is 2.29. Let us randomly pick another one, iron, let's say 2.61, 2.88. And another one may be aluminum 2.14 and 2.19. So what you see is that, and if you just scan through, this column and this column, what you find is that all the numbers are pretty much the same. I mean, 2 point something here and there. In units of course, 10 to the minus 8. There's a factor of 10 to the minus 8 here. So 2 point something into 10 to the minus 8 watt ohm per Kelvin square is the number for all the metals, and at both 273 Kelvin and 373 Kelvin. So what you conclude from here is that kappa over sigma is proportional to temperature for a metal, and this proportionality is the same roughly for all metals. Now, that's a striking thing, right? This number is firstly proportional to kappa over sigma is proportional to temperature, and this proportionality is the same for all metals. So the task that we'll undertake now is to sort of explain this using the Drude model. Okay. So first thing we'll do, we have already calculated sigma. Right? The n is square tau over n. We calculated that. So our task here first is to get an expression for kappa. So what is assumed in the Drude model? See, Drude model is all about the theory of electrons in a metal. It just treats the ions as some, stationary background from which the electrons experience occasional collisions. But apart from that, they don't play any role. So therefore, it's assumed that the electrons carry all the heat. The thermal conductivity is because of the electrons. And which sort of makes sense because for ages we have known that metals are good conductors of electricity, heat. So therefore, you assume that it's the electrons that carry the thermal current in a metal. Now, let us consider a sort of thin metallic bar. And let's say if you heat one of the ends compared to the other, so we apply some heat, just hold a burner below it or something, its temperature will rise. And then if you remove that source of heat, of course, what will happen is that extra thermal energy will flow from the hot end to the cold end, and eventually the two ends will come to the same temperature. So that is what we all know. But that is not what exactly we are thinking about here. So what we are thinking about is, so that will not give you a continuous flow of heat energy. So what we are thinking about is a situation where there is a source of heat at one end. You put in contact with something, and the other end is in contact with something colder. And so there is a flow of heat, and the rate of flow is compensated exactly by the amount of heat that's being supplied to the hotter end, so that you maintain this steady state. So we are interested in a steady state where there is a steady temperature gradient which is not changing with time, and there is a constant flow of heat energy from the hot end to the cold end. So in that steady state situation, we have, and if the temperature gradient is not very large, then, as we usually do in almost everything is in physics, is that we assume that the effect that we have, that is the flow of thermal energy, is to the leading order proportional to the cause that is responsible for it, namely the temperature gradient. So the flow of thermal energy is proportional to the temperature gradient, that is gradient of T, and so that's that relation that we wrote earlier, this one. So that's a general expression for a 3D system, 1D, 2D, 3D, whatever. Let us take this simple 1D example to understand the things and work out the expressions. So here is the hotter end. So we are supplying heat to this end, and this is the colder end, and there is a flow of heat energy, thermal energy from this side to that side. And in a 1D system, it's only along x, so J of Q is minus kappa dt dx, and there's a minus sign so that kappa would turn out to be a positive number because the the flow of heat would be in a direction opposite to the temperature gradient. Okay, so suppose now we focus on a particular point x. Let's say this is my point x, okay, the line I have drawn here. Now, what is happening at this point? There's only flow of heat energy. We don't assume any flow of charge current here. So the charge current is 0 at that point. So equal number of electrons come and pass from left to right and from right to left, so that there is no net charge current. But then how do you get the heat current? You get the heat current because the electrons that are coming from the hotter end carries larger thermal energy. That's how you get the heat current. But the numbers are same in either directions. If that strikes you, this sort of an assumption, if that strikes you as sort of odd and offhand and crude, it is. This is a rather crude assumption, but that's how things were worked out, and we will work with that within this with this assumption and see what we get. So again, so what is the assumption? Equal number of electrons are coming from the left and the right. So if n is my electron density here, sort of n by 2 of them come and pass from this side to that side, and n by 2 from this side to that side. Okay, given that assumption, let us see what is, so how much, what is the velocity they come with, what is the energy they come with? That depends on them. Yes.
So you have written at point X, half of the electrons come from the left and half of them come from right. So isn't there a charge accumulation at that point?
No. These are flowing electrons, right? So half of them come from the left and go to the right. Half of them come from the right and go to the left. And we are looking at a slice perpendicular to this direction of flow at the point X. So equal number of electrons flow from left to right and right to left. So the net charge current is 0.
Okay, but isn't this experimentally, because when we touch, let's say, a hot object, we don't usually get a shock?
Yeah, that's what shock. Yeah, that's what I'm seeing.
Yeah. So okay.
you may get a heat shock, but you don't get an electrical shock. Yeah. Right. So yeah, that's exactly what I'm saying, because there is no net flow of charge.
Okay.
Right? Do you agree with that?
Yes, sir.
Okay. That's an assumption. And we'll sort of elaborate it a little bit as we go along. So after that, what I'm trying to say here is that then now consider the electrons that are coming from the left, which is the hotter side. Okay. So how much energy do they carry? Depends on remember this, one of the basic assumptions of the Trude model, that electrons, the thermalization of the electrons happen through these collisions with the ions, and if the electrons collide with ions in a region which is hotter, they have higher velocities and carry more thermal energy. So that's the idea one is going to use here. So electrons that are coming from the higher temperature side, on an average, have had their last collision at some point x prime, which is, if this x is my point of interest, then they have had their last collision at a point x minus v tau. Now tau is this relaxation time. And on the other hand, electrons arriving at x from the right, that is the low temperature side, on an average, have had their last collision at x plus v tau. Okay, these are again some very crude assumptions that are made to work things out. Okay, now having made those assumptions, yes, go ahead.
So should the V's be equal? Because we realize that after collision, they take V's such that it is corresponding to the temperature. So one side is colder, one side is hotter.
Yes. So that's a very valid point. But again, as I said, these are very crude assumptions, and these are the crude assumptions that are made here. But that's a valid point, and you can actually work it out if you assume these velocities to be different, and you'll find that it makes a small difference to the result. Maybe I'll ask you to work it out. But at this point of time, the assumption is that the velocities are the same. But what is different? I mean, something has to carry excess heat energy from one side to the other, and that is the next point. So if you look at this line here, so let us assume that if T is the temperature at in some region, and electrons colliding with ions in that region, let epsilon T be the average thermal energy of those electrons. Okay. Now T, of course, here is X dependent. So okay, so what one is saying is that suppose if the whole metal is at some temperature T, then average thermal energy everywhere would be epsilon T. On the other hand, if there are two regions, let's say T1 and T2, then electrons colliding with ions in this region over here, which is at temperature T1, would carry average thermal energy epsilon T1. And this electrons colliding in this region would carry average thermal energy epsilon T2. And if epsilon T happens to be a function of X, then of course it depends where they last collided with ions. So if the temperature, as I said, at a point is X, then average thermal energy of electrons that had their last collision at that point would be epsilon T of X. Okay. So then with these assumptions, then what is the contributions of the electrons, left to right electrons and right to left electrons, to the thermal current? So first, let us look at the contributions of the electrons that are moving from the left to right. Remember, left was our high temperature region, and the right was the low temperature region. So J plus, I'm calling the current, thermal current from this side to that side in the positive X direction. So J plus is the number density of electrons that come from that side, n by 2 times V, and then epsilon T at X minus V tau. So which is, as I said, the current J plus is the number density of such electrons that come from the left times their velocity times the average energy such electrons carry. By the same argument, the contributions of electrons that come from the right, the low temperature region, to the thermal current would be, I call it J minus, is n by 2V, and epsilon corresponding to temperature at point X plus V tau. Okay, so what is the net current? The net current is J plus minus J minus, because J plus is in positive X direction, J minus is the sort of magnitude of the current in the negative X direction. So you take J plus minus J minus. So you write these two expressions, and then you expand these epsilon Tx minus V tau around the point X. So you'll get some del epsilon del X, which you write as del epsilon del T del dt dx. So this is, trivial bit of algebra here, which I think you can easily figure out. So when you do that, eventually what we'll get is JQ is n V squared tau d epsilon d tau times minus dt dx. So this is for the simple one-dimensional example that we do. So how do we write things for a general three-dimensional solid? Well, we realize that average of all these things is 1 over V squared, right? So if this V squared is the sort of average thermal velocity, then each one of these is 1/3 of that. So that is one point. The next point is that we can write N. So N is the electron number density. Epsilon is the average energy per electron. So we can write this N d epsilon dt as N is simply capital N, total number of electrons divided by the volume, d epsilon dt. But then capital N times epsilon is the total energy of the electrons, which is, I write as this capital E. This is not the electric field. This is the total energy. Now dE dt is 1 over V dE dt is the specific heat per unit volume, right? So part of this quantity is just the specific heat of the metal. So if you use that information, so what you have is J of Q is just 1/3 V squared tau times CV times, there should be a vector here, this is a vector, minus the gradient of temperature. So we have got an expression. So let me just correct that quickly. Okay. So we got an expression for JQ, which is proportional to gradient of T. And from that, we can, of course, write this proportionality constant as kappa, which turns out to be 1/3 V squared tau times CV, which is equivalently 1/3 V. LL is the mean free path, remember, times CV. So we are happy. We have got an expression for the thermal conductivity of metals. And so let us now have a look at the Wiedemann-Franz law once again. By the way, that observation that the ratio of the thermal conductivity and electrical conductivity of metals is proportional to the temperature. And yeah, it's sort of same, more or less, same for all metals. That's called the Wiedemann-Franz law. Okay, so what is the ratio then? Here is the ratio. Kappa is 1/3 V squared tau CV, and sigma, remember, is N is square tau over M. So you cancel tau, etc. This is what you get: 1/3 V squared M CV over N E squared. So then, is it proportional to the temperature? So what are the temperature dependent quantities here? Obviously not N or E squared. Given the metal, N is a constant, E and M are, of course, some fundamental constants of nature. So V squared and CV, these are the two things that are dependent on temperature. So so now let us try to estimate these in terms of temperature, and that's why the classical approximation of the electrons come in. Electrons are classical particles in the Drude theory. So therefore, half mv squared is 3/2 kBt, and CV is 3/2 nkB for an ideal gas. That's what Drude used. So you plug those in, and with all of that, what we'll get is kappa over sigma is 3/2 kB by E squared times T. Exactly what, I mean, at least you get something which is proportional to T. And then, of course, you can also figure out what kappa over sigma T is, and you get this number when you put the values of the constants in. You get 1.11 into 10 to the minus 8 watt ohm per Kelvin squared, which is about half of what was seen in the experiments. The experiments found 2 point something. So now there's a curious bit of thing here. In his original paper, now again I have not read Drude's original paper. That was probably be in German. But nevertheless, Ashcroft and Mermin's text will tell you that in his original work, he had got a spurious factor of 2 or half in the expression for sigma. And there's a reason to that. Probably we'll work it out in one of the assignments. So he had got a factor of half in sigma, which would, so if you, instead of sigma, if you had sigma over 2 here, your value for kappa over sigma tau would become double of that. So he got a value of 2.22 into 10 to the minus 8, which is, amazingly close to the experimental value for such theory. So this, of course, was considered to be a great triumph of Drude theory, which sort of generated further interest in it and so on. So now we realize, so there was this accidental factor of 2, which led to this striking similarity with experimental results. But also there are other issues here. Now, once the experiments were done to measure the specific heat of metals, it was found that at room temperature, there was no contribution of the order of 3/2 nkB. In fact, the electronic contribution to the specific heat of metal at room temperatures is very, very small. It's not anything significant, number one. Number two, after the quantum theory was worked out, it was also realized that this I mentioned in the last lecture also, the velocity that Drude estimated from this classical equipartition theorem is also way too large, way too small. So his estimate of CV was too large, his estimate of V was too small, and therefore there was an accidental, and they were large and small by the same orders of magnitude. And therefore, there was this accidental cancellation, which led to a striking agreement with the experimental results for kappa over sigma. So, what is the moral of the story? The moral of the story is that you can get perfectly right results for completely wrong reasons. And it happens in other places, or has happened in other places in physics also. So, don't get too excited if you get the right result. You should try to ensure that why you are getting, or try to understand why you are getting the right results. Should you really get the right results? But anyway, I guess in Drude's time, he didn't have the sort of knowledge of quantum physics to sort of check these things, but we'll study them as we go along. Okay, so that's about the Wiedemann-Franz law, and as I said, for completely wrong reasons, Drude theory was in very good agreement with the Wiedemann-Franz law. But this brings us to the question that who asked it? This is the problem. I forgot who asked the question, but nevertheless, there is this question of velocities. Why should the electrons coming from the hotter side and the colder side should come with the same velocity? Yeah, that's a good question. So what happens is that, well, when you first set up these temperature difference between the two ends of the metallic conductor, then of course the electrons from the hotter side would come with a larger velocity, and so there would be more electrons coming from the hotter side going to the colder side. But then what does that do? So if there are more electrons going from the hotter side to the colder side, that would accumulate some charges. On one side would accumulate negative charges, and the other side would accumulate positive charges. And these experiments in which you are heating one side and the other side is cold, and you are sort of measuring the thermal current, there's no electrical circuit. Okay, so the electrons can't flow back. So there'll be some accumulation of charges, which will set up an electric field, but then that electric field would sort of resist the motion of electrons. It would be in the direction, in a direction so that it opposes the motion of this preferential flow of electrons in a certain direction. So it will set up a potential difference between the two ends. And this is exactly what is, you may have studied, is called the Seebeck effect. So there will be an electric field or a potential difference across the two sides of the metallic conductor. So we'll have an electric field which is, again, we assume, proportional to the temperature gradient. And the proportionality constant Q is called the thermopower of the metal. Now this, so this generally this area of thermoelectricity is a very important and very active area of research right now. Although I don't know the sort of technicalities of it, but I can tell you why it is considered to be very important and useful. In many applications, many industrial applications, in our ordinary, like for example, motor vehicles that we use, a lot of heat is actually wasted. So the sort of idea for technology is that if you can use, so suppose you have something that, some material, one end of it is getting heated, the other is not, and so on. So there's a potential difference that is being generated, and whether it can be put to constructive use. And so therefore you want materials that have large thermal power. So this quantity Q. So that's why it is considered to be technologically important. And what we'll do here is look at a very crude theory of thermal power of metals. But right now people are working out much more sophisticated, fully quantum theories of this thermoelectricity.
So, are you saying that this temperature gradient is like producing a density gradient in electron, like the field of electrons? Like the density
could you repeat your question?
Like, how is this electric field generated? Is it due to the density gradient of like electrons?
Yes.
But like, although like there's a velocity, like difference in velocity at different positions, the velocity themselves are random, right? So why should they cause a density gradient?
Okay, let us go back to this and try to answer your question. So let us think of a one-dimensional thing, okay, for simplicity. So you supply heat and put it at a higher temperature and descend at a lower temperature, right? So initially what will happen is that there are electrons in this region will come with higher velocities because the temperature is higher here. So they will move faster. So let's say if I consider the middle, then there will be more electrons sort of in any interval of time, there will be more electrons sort of passing from this side to that side compared to electrons passing from this side to that side.
That's what I'm saying. That is not the case, right? It is not the case that the electrons, more number of electrons are passing from left to right. That was the argument in the model that you were discussing for thermal conductivity. At any point, equal numbers of electrons are passing from left to right.
Yeah. So I'm trying to distinguish I'm trying to distinguish these two situations now. Yes, while calculating the thermal conductivity, we assume that equal number of electrons come from both sides. And I repeat, that is an assumption which is good when you have reached the steady state. But what is the steady state? Now I'm talking of the situation when you have, let's say, just set up the temperature gradient. Okay. In that situation, the electrons on the left have higher velocities, so they would sort of move faster. And if you move faster, if they move faster, so what is the number of electrons moving or crossing a unit area in time dt? Well, area is not a very meaningful thing if we are talking of a one-dimensional thing, but what is the number of the number of electrons passing through it in unit time? That would be proportional to proportional to dt times their velocity, right?
Yeah.
So if the velocity is higher on that side, more electrons would pass from this side to that side. If the velocity is lower on this side, less number of electrons will come from this, pass from this side to that side. Now, what does that do? That accumulates more electrons on this side. And if you accumulate more electrons on this side, that sets up an electric field, right, which will oppose the motion of subsequent electrons. So eventually you will reach a steady state where there will be equal number of electrons flowing from left to right and right to left. And that happens after the steady state has been established, in which case you have an electric field set up within the metal because of this charge separation. That happens because of the thermal gradient, the temperature gradient that you have set up. And that's precisely what is Seebeck effect.
Sir, isn't that a second order effect? I mean, if we consider the continuity equation for such a process, then this rho in the continuity equation is like this density, electron density, and this J is the current. Then we have expressed J as gradient of temperature, so divergence of that will be the second order Laplacian kind of a thing.
Yeah, but the point is that it happens because you have set up a temperature gradient, right?
Yeah, so in steady state that will go away, right?
No. We are calling the steady state when you have flow of thermal current, but not electrical current. Or, in other words, how should I put it? Okay, why don't I go through the rest of it? Maybe it will answer your question already. Okay, because what we are trying to say is that in the steady state, these thermal currents and the electrical currents should balance each other. Okay, so let me just go through the analysis. Maybe it will already answer your question. If not, we'll see it at that point of time. So what is the assumption here is that the electric field is some constant times gradient of t. So now we write this velocity because of the thermal gradient, the temperature gradient. So what is the mean velocity at some point x? The mean velocity is, see, this Vx minus V tau. Remember earlier we were writing the mean energy of the electrons when we calculated the thermal current. Now we are talking of the mean velocity, and we are distinguishing between velocities of electrons that come from the left and the velocities of electrons that come from the right. And this one, Vx minus V tau, is the mean velocity of the electrons that come from the left. So this is it, minus the velocity of the electrons that come from the right. So this is my mean electronic velocity at x. And then if you just expand this around the point x, you can write this as tau v dv dx, which of course is minus tau d dx of v squared by 2. Yeah. So therefore, again, this v squared is written as 1/3 of the average velocity in a three-dimensional solid. So then vq is minus tau over 6 d dx of v squared, and this d dx of v squared is written as dv squared dt and dt dx. So that is simple.
How is it tau over 6?
This factor of 3 comes from this one. I showed you earlier, this one.
Oh, achha.
See, this velocity, this mean velocity in a three-dimensional solid is what we get from equipartition, right?
Yes, okay, fine.
Okay. So this is the sort of vectorial expression for that. And the mean velocity of the electrons due to the electric field is this. And this electric field is not an external electric field. This is what is set up within the system. And then what we are saying is that in the steady state, the net current is 0. Any excess flow of electrons in one direction due to thermal gradient is exactly balanced by excess flow of electrons in the due to the electric field that has been set up. So these two cancel. What is not cancelled is the net flow of thermal current. As I say, these assumptions, particularly when we derive the thermal current, the assumptions are very crude. And I request you to go and read the actual text of, because I don't want to, of course, read out all that they have written, but it's a very nicely written text. So you should read those arguments to understand that, there are some, these assumptions are very crude, that, I consider only, while calculating the thermal current, I consider only the mean energy and not the velocity. But as I said, you can figure out what will be the change to the thermal current if you also consider the velocity difference from the two ends. But here what we are doing is we are saying that this rate of flow of number of electrons due to the temperature gradient and the electric field that has been set up cancel each other in the steady state. That's what I call the steady state. So this is what my condition for steady state is. And then what you do is you just say this plus this equal to 0. And that will give you an expression for Q. Because Q, remember, is the proportionality constant between the electric field and gradient of T. So you will get Q as this tau over 6em dv squared dt gradient of T. So again, this can be written in terms of specific heat, because this d dt of mv squared by 2. See, remember, this is in terms of thermal energy. So this can be written as Cv over 3me with a minus sign. Okay, so we have got an expression for the thermal power. How do we do? I mean, how does it compare with experiments? So let us look at some numbers. Yeah, so here are some numbers. So if you so this is the expression we obtained. So you can write Cv in terms of n kb, 3 by 2 n kb, and so on. So you'll get this. So it's a constant, okay? And that constant is this 10 to something times 10 to the minus 4 volt per Kelvin. And the experimental numbers for metals are microvolts per Kelvin. So the experimental numbers are actually something like 10 to the minus 6 volt per Kelvin. What we are getting is 10 to the minus 4, 10 to the minus 5 volt per Kelvin. So obviously we are 1 to 2 orders of magnitude off. And that's precisely because of the overestimation of CV, as I mentioned earlier. While calculating these kappa over sigma ratio, these wrong estimations of CV and the velocity sort of cancelled each other. So therefore, Drude got a right answer for completely wrong reasons. However, there is no such cancellation here in case of Q, and therefore this discrepancy shows up, and we are orders of magnitude off. Okay, so that's the limiter. So that obviously tells you that there are serious limitations of the Drude theory, and with hindsight of more than 100 years, we know that simply because the classical theory is not applicable to a system of electrons inside a matter, and we have to do better. We have to apply quantum theory. So that concludes our discussion on Drude theory. After that, we'll go over to discussion of quantum theory of solids. And so do you have any questions, concerns at this point? Otherwise, we'll sort of end this here and start with a new topic.
Sir, I have a question from equation 1.42.
1.42 of what? Ashcroft and Marvin?
Yes.
Okay, let's see what is 1.42. Here.
Yeah, so that.
Yeah, actually, I did not discuss this part, yes.
So actually the claim is that they can write the separate equation, the separate continuity equation, and for the positive charges and negative charges. So that's how they derive the whole thing. So my question is that, is it valid?
Where does it say the second important the electron gas conserving charge density? Do they actually, in this chapter, do they actually talk about continuity equation for positive charges at all? I thought the whole discussion was about electrons.
So yes, so my question is that, and to prove this whole thing, and we need to write the Gauss law. I mean, we need to use the Gauss law, and so we already assume that the total charge density was 0. So, so divergence of E will always be 0. So then the
no. This entire expression. See, I have to again see because I have not recently read this part, so I just looking at these expressions. What I see is that all that they have written are for the electrons. There are no discussions about the positively charged ions at all. In fact, apart from that, the electrons collide with them occasionally. They don't even come into the consideration.
Yes,
the entire discussion is on electrons, and this electric field that they are talking about in this equation 1.43 is what due to the electrons with charge density rho.
Yes, so my question is that writing equation 1.43, is it valid? I mean, the left hand side is the left hand side the electric field is for the total charges, and on the right
no electric field is not for the total charges. No, I don't think so. It's for the electrons.
So even if in the system we have electric field for the positive charges and also for the negative charges, and can we write separate Gauss laws for positive charge and negative charge?
See, as far as I understand, in this entire analysis, they don't even worry about the positive charges.
No,
I mean,
actually,
Druday's analysis. By they,
no,
I mean
actually that is taken into consideration. If you see equation 1.31.
See, Manojit, I don't remember the sort of subtle arguments that have gone into this because I have not looked at it lately. So if you suddenly open this in front of me, I may not be. I probably see the electrostatics part of it is pretty straightforward. That is not the point of discussion. The point of discussion is what exactly went into Druday's assumption. So that I cannot comment on right now because I have not read this part very recently. So maybe we can discuss it at some other time. I mean, later on, after I have looked at it.
Oh.
Okay.
Sir, about that 1D 1D heat transfer. So you were saying that after when steady state is achieved, the lower temperature part means that side has a higher accumulation of electrons, and the other side has a lower accumulation electron, so there is a potential. So when we exploit this as an energy, as an electric source, as a battery or something, so then again this steady state is broken because electrons go out and from that side to the other side. So then is the steady state broken?
Well, that's more of a technology question. Well, I don't know. You have this potential difference set up between the two ends. Now, if you sort of, and this potential difference will be maintained in some sense because the heat is being constantly generated, right, in whatever process is going on. And then if you have an external circuit, which through which you can drive current because of this potential difference, then it serves your purpose, right? That's the in principle understanding. Right? I mean, you have these two ends of the metallic conductor, which are at different potentials because there is a temperature difference, which is maintained because there is some process going on which creates this temperature difference. And then if you have an external circuit through which this can drive current, then that's a sort of productive utilization of that temperature difference.
I mean, if we continually maintain the temperature difference, then I think it is viable.
Yeah, that's the whole point. That's the whole point, right?
Okay.
That's the whole point. Because your industrial processes or your car engine, I mean, they are running, let's say, more or less continuously. So heat is being generated, and so therefore this potential difference is being maintained. And you have an external circuit now through which you are driving current because of this potential difference. That's the idea. That's the sort of in principle idea. Okay, so if there are no other questions, we'll now move on to something. But before we go on to discussing the sort of quantum theory of electrons in solids, I just wanted to go through one slide to give you a background of the diversity of properties that you have in solid systems. Just from a theoretical perspective, how challenging it can be to study these things. So let me see where I have it. Yeah, so just for fun, I collected some information about physical properties of different types of solids. And these are not all periodic solids. Some are periodic solids, some are not periodic solids. For example, rubber and glass and Teflon, these are not periodic solids. On the other hand, even, I don't know about chalk and limestone. They're probably periodic solids. But Teflon and glass and rubber are definitely not. So I've just listed 3 properties. And so they will already give you an idea. So for example, if I look at bulk modulus, they are not terribly different between different solids. But
sir,
still,
we are actually seeing the old slide.
What are you seeing?
I mean, the Drude model slide.
Oh, I see. Just one second. Okay. Let me see if it works now. Do you see a table now?
Yes, it's visible.
Okay. So the bulk modulus, for example, it can go from in units of gigapascal. It can go from 1 to 160, 440. Diamond is one of the hardest materials. So, you see 2 orders of magnitude. Melting temperature, again, diamond has one of the highest melting temperatures, diamond and graphite. Again, about 1 order of magnitude. But the most striking thing is electrical conductivity. We have been talking about conductivity, and it's good to have some sense of these numbers because, when you are doing solid state or condensed matter physics, having a sense of these numbers are sometimes important. So let's see. For the typical metals, you have the order of 10 to the 7, and that can go as low as for Teflon. If you look at the numbers, that is 10 to the minus 25 to 10 to the minus 23 to 25. So you see there are 32 orders of magnitude different in everyday materials that you see around. And it's rarely that you have, physical quantities in things that you see around you that are such hugely different. So explaining such differences, understanding such differences, of course, a challenge. And it's exciting also. So can you calculate these things? So just to give you a sort of feel for numbers. So how would one try to answer these questions? So why is, for example, diamond so hard with a bulk modulus of 443 gigapascal, whereas Teflon is only 1 gigapascal? Or something is, I don't look at glass, let's say sodium chloride, which is somewhere around 24 gigapascal. Or diamond has a melting temperature which is 4,000 degrees Celsius, and something else melts at 900 degrees Celsius. So of course, it has to do with the bonding in these systems. And we go into, now that you know of atoms, and now that you know that atoms form some sort of chemical bonds to form these solids, the intuition would of course be that it has to do with the bonds. If the bonds are stronger, the material would be stronger. If they are not, the material would be sort of softer, have lower bulk modulus, and presumably would also have lower melting temperatures. So how would you go about describing these bonds within a solid? And so that is one thing. Or how would you calculate, or what would be calculate or understand what is electrical conductivity or thermal conductivity of a metal? We have been talking about these things. As we found, the classical theory is not adequate, so we have to develop a quantum theory. Now, if I were to start from the basic quantum theory, I mean, we know that, if we have a quantum particle or a set of quantum particles experiencing some potential, then in order to describe their evolution, we have to solve the Schrodinger equation for them. So if that, so, ideally, that's the point one would like to start from. Okay, so I have a solid which has electrons and ions, negatively and positively charged respectively, and they interact with each other, and we know how they interact with each other through Coulomb interaction. And this is how then I would write down the Hamiltonian, for the entire system. This is the Hamiltonian. The first term is the kinetic energy due to all the electrons. This sum over small I goes over all the electron indices. Capital I is the index over all the nuclei. Okay, so that's the kinetic energy of the nuclei. This third term is the interaction energy between the electrons and the nuclei. This attractive Coulomb interaction. This term is the electron-electron interaction, repulsion. This is the ion-ion repulsion. This should actually be the index here. So this is the ion-ion repulsion. So we know that. We can write it down. But solving such problems is notoriously difficult, and we won't even go close to that in this course. Although these days we can solve such equations within certain approximations. But the simplest theory one can start from is you just forget all the terms except the first one. So you consider only the kinetic energy operator for the electrons. In other words, you consider the electrons to be free particles inside the metal. So what Drude did was to consider electrons as free independent particles, free in the sense that they don't interact with anything else, independent in the sense that they don't interact with each other. We are carrying forward those same approximations, but the only difference we are making, and that's of course, as we'll see, already makes a significant difference in our qualitative understanding of things as well as quantitative understanding of things, is that the electrons are not classical particles, they are quantum particles. Okay, so the problem at hand is that of a set of quantum particles, free quantum particles that are moving around in the volume of the metal. One crucial ingredient in this theory is that the electrons are fermions. So therefore, when we consider many electron states, we have to respect their spin in the sense that only 2 electrons can be put in a particular quantum state. Okay, we have an infinite solid in which we have these free electrons. They are free because they are not interacting. So we have forgotten all about the nuclei. The electrons are not interacting with the nuclei. They are not interacting with each other. They are independent. But how do we treat, again, the same question that we discussed when I suggested this, the first assignment to you, is that how do we treat this infinite matter? Okay. So let us go again to the discussion of this boundary conditions. Okay, suppose this is a piece of metal that I have. And my electrons are moving inside this region. What would be, I'm not interested in the boundaries. I'm interested in the properties of the bulk of the metal. So what happens in this region? Again, some sense of length scales are important here. So as we know, the atom-atom difference inside a metal is of the order of angstrom. So therefore, even a micrometer, millimeter sized metallic piece is a huge thing compared to atomic length scales. So we are interested in what is happening, what are the properties of the electrons deep inside the metal. We are not interested in what is happening near these boundaries. So how do we construct my theory? I mean, solving this kind of a problem where I have some free particles is not difficult at all. We have solved particle in a box problem. So I can do the same thing here. A three-dimensional box. I'll consider my metal to be three-dimensional, of course. So particle in a three-dimensional box is a sort of trivial mathematical problem to solve. The only question is, what is the boundary condition that I should apply? One possibility is to treat the boundaries as hard boundaries, so that, as you do in a particle in a box problem, the potential is infinite outside. So therefore, all the wave functions, let's say, should vary. If this is my x direction, I can demand that the wave functions should vary at this boundary and that boundary. There are two problems with that. One is that you will start getting, stationary solutions, which you are not interested in because of these hard boundary conditions, number one. Number two, in a real metal, the wave functions do not vanish exactly at the boundary. Of course, depends on what exactly is the boundary. Is the last sort of layer of last plane of positively charged nuclei your boundary? Mathematically speaking, if that is what you call your boundary, then the electronic wave functions do not vanish exactly at the boundary. They spill out of the boundary. So you should then consider that this is a finite piece, and your wave functions vanish only when, let's say, x goes to infinity, y goes to infinity, and minus infinity, and so on. So that would complicate your analysis of the problem. That is where the periodic boundary condition is much more convenient. I have already discussed this. So what you basically do is wrap around this side and connect it to this side. So what that does is completely does away with the boundaries. There are no boundaries anymore. Things are wrapped, the system is wrapped onto itself in all three directions. And so therefore, I showed you pictures of that. In 1D, I had a straight line. I bend it and connect it to this side. So what was a straight line now becomes a circle. If I have a 2D square, I wrap this side to that, this side to that. And what you would end up getting is a torus. It's not easy to visualize what would happen in a three-dimensional space, but the mathematical idea is just the same. So that's why the periodic boundary condition is the most convenient thing to use when you are dealing with systems that you want to treat as essentially infinite, and you don't want to bother about their boundaries. And this periodic boundary condition will keep coming back to us. Okay, so let's see what I want to discuss next in this. Okay, so what is the problem we are solving then? I'll just type it in a few things here. Oops, that. Okay, so there should be a square. So I want to solve that problem with the boundary condition that, okay, so that's the problem I want to solve with the boundary condition that this. And this same boundary condition would be repeated in the other directions also. That is, psi of x y plus L would be equal to psi x y z. So this would be same as psi x y plus L and z, which is equal to x y z plus L. In other words, I'm considering the electrons to be confined in a big box, let's say, and then I apply these periodic boundary conditions. So, I hope I don't have to solve this kind of a problem, which is straightforward. So what you will have is psi of R is equal to you get solutions like this with the normalization. This. And so, okay, let me just, for the sake of completeness, I write down the energy expression. So that's the energy that we have for a particular K. And these wave functions, as you know, I mean, this sort of wave function comes from this so-called box normalization of free particles and so on. And then these wave functions are both energy. So this is the value of the energy. These are energy eigenstates and these are momentum eigenstates. So there's nothing to be sort of mentioned there. So what is important next is that what are the values of K? So this K index that comes in, which defines the energy and the momentum. Momentum for such a state is H cross K. So what are the allowed values of K? So if I just look at, for example, the X part of it, what I'm saying is e to the I x plus L is the same as e to the x. So that would imply that e to the I L, so there was a k over here. Okay, so e to the I k kxl would be e to the I 2 pi n, which would give you the allowed values of k. So for example, kx would be where n's are integers. Okay, and similarly, you will get values for ky and kz. So as we'll see when we study the periodic solids also, where the lattice structure is taken into account, this sort of kx, ky, kz, they will appear there as well. And so these are the allowed values of kx, and in the limit that L is very large, we can consider k to be essentially a continuous index. Okay, but so how much time do we have? Okay, the next thing to figure out is what are the sort of density of k points. So, I can think of a k space, right? I can think of a k space given by kx, ky, and kz indices. So I can think of a k space given by kx, ky, and kz indices, and what is useful to figure out is sort of what is the density of points in this space. So let me just maybe directly show you this picture that that will be easier. Yeah. So, so here is a picture of the kx, ky space. So we figured out that the values of kx, let's say, is twice pi nx over L. So n is, let's say, 0, 1, 2, etc., -1, -2, and so on. And you get values of, allowed values of kx. So if I write these values, so here is allowed values of kx. The next value would be twice pi over L away. The next value would be another twice pi over L away, and so on. And similarly for in the y direction. So I get this sort of grid of points in the k space, and I ask what is the sort of volume of each one of these points. Okay, so a point appears a distance twice pi over L distance away. So in a one-dimensional space, there is one k point twice pi over L distance. And so each point sort of has twice pi over L volume to it. That's in one-dimensional space. If I'm in a two-dimensional space, each point has twice pi over L squared area to it. If I'm in a three-dimensional space, then each point has twice pi over L cubed area to it. In this k space, remember. So So this is an important point to realize, that each point has twice pi over L cubed volume to it. So if there is a total volume of omega in the K space, the number of K points will be, of course, the total volume in K space divided by the volume per point. So if, let's say, omega is a volume in K space and twice pi over L cubed is the volume per K point, then the number of K points in a volume omega in the K space would be omega divided by this, which is omega V. V is the volume of the real space system. So if we are talking of a metal of volume V, then V is the volume of the metal that I have, which is the box L cubed. So L cubed is V. So omega V over 8 pi cube. This is the number of K points in a volume omega of K space. Remember, I repeat this, omega is the volume in K space, V is the volume in real space, and the number of K points in a volume omega in the K space is this. So if I ask what is the density of K points, that is number of K points per unit volume in the K space, it would be this number divided by omega, so which is V over 8 pi cubed. So that is the sort of density of K points in the K space that we have. Okay, so I think after that, I think it is already past 12:30. Maybe this is a good point to stop here. So once you understand this much, then, by the way, have you done these things in your statistical mechanics course?
Yes.
Yeah, we have done it for
you have done it. So do you think sort of detailed discussion is required, or how comfortable are you, or would you like to still, like me to go through it?
Yeah, if you discuss the conclusions, I mean the graphs, the conclusions about the specific heat, this type of things, that would be sufficient.
Okay. Okay, so I'll take up from here and focus on the sort of. So this sort of how you calculate the Fermi sphere, volume of the Fermi sphere, Fermi velocity, and so on. All these things you are familiar with, is it?
Yes, we have done in StatMech course.
All right, so maybe I'll just skip those or quickly go through those and focus on the physics part of it. All right. Okay then, so we'll take it up from here on Friday. Are there any other questions today?
I have just one more thing to say. So is it possible that you can use the board from the next class?
No, that's what I wanted to do in this part. But as I said, this coupling of my iPad with the laptop, it worked till this morning when I tested. But then just before the class, it stopped working. You just saw a blank screen or black screen. So there is some technical issue here. So this iPad camera is good enough, I believe, for you to see the board clearly. That's what I wanted to do. But also, again, sitting in my, since I'm giving these lectures from my office and I have a small board in my office, I cannot do the full board work that one normally does in a classroom, because there I have some 3-4 boards available to me. So all those things will be difficult to do, but at least some crucial parts I wanted to show you, which didn't work out the way I had wanted. But I must also tell you that so far we haven't done any serious algebra. And in fact, first half of the course, or maybe even more, we won't have any serious algebra. It's only when we get to discussions of magnetism, I think, when some serious algebra will come in. So therefore, I would ask you to focus more on the physics concepts of it and work the algebra out. And I would again repeat that please read the textbook because the concepts are very well discussed there. We are discussing it in the class. So read through the text. Algebra is minimal in this part. Work that out yourself. I don't see any reason why you can get stuck with the algebra. In fact, I would say that if you are comfortable reading through the text, you can learn all of these things even without me. If you can read through the book. Anyway, so we are discussing those ideas in the class, and then the algebra, as I said, is minimal in this part, so you should be able to work it out. We'll get to serious algebra when we discuss magnetism. Okay, so if there are no other questions, then I'll stop it now.
So, is this meeting link fixed or will it keep changing?
Was it Harshit?
Yeah.
Can you speak a little louder? I can't hear you very well.
I'm asking, is this meeting link fixed for rest of the classes, or will it keep changing?
You mean the timing?
Meeting link.
Oh, meeting link. I don't know. I would prefer to send you the link just the night before or just before the class every time.
Okay.
Okay then. See you on Friday.